Hello, sixth graders. This week we are going to continue talking about weather. I hope you guys had a great weekend. It was kind of nice to have a extra couple of days in there, I hope. So we're going to continue with the ed puzzles and stuff. One change, I'm going to start grading the ed puzzles a little bit harder, I guess you would say. I see some people are usually putting in the most effort that they can, but some people kind of just skim through and are getting like 30% on the answers and stuff. So I want the people that are doing better to be graded as such. So make sure you're trying your hardest on the ed puzzles. This week we are going to talk about pressure and how pressure relates to what we're talking about. So let's go ahead and get started. So first thing, what is pressure? A lot of you guys have a good understanding of pressure. It's kind of like weight, but it's a little bit different. So what it is the amount of force that the air is pushing, right? High pressure would feel like someone's like pushing down on you, right? Low pressure would be not pushing down as hard, okay? If you look at this picture here, this column you can think has more dots, which would be more air particles, than this column. So this column is going to be heavier and have more pressure. This column here doesn't have as many dots. It's not as heavy. It's going to have low pressure. So here's a couple of big things. Dense air, dense meaning there's more molecules, has more pressure. Okay, this is like just more weight, more pressure, dense. Light air has less pressure. So if you have lighter air that's not as dense, it's not going to have as much weight. It's going to have less pressure. Sinking air is dense, so sinking air is high pressure. Rising air is light, less dense, so it's going to have less pressure. It's going to be low pressure. So, big thing, sinking air is high pressure, rising air is low pressure, okay? Let's just take a peek at this picture really quick. So, this can be applied to a couple of things on Earth. So if you just want to think about just air pressure alone, if you're higher in altitude, you have lower pressure, right? So if you go from ground level here in Minnesota and you go 10,000 feet up in the air, like maybe a mountain in Wyoming, if you bring like a water bottle, you can tell that there's a difference in air pressure really easily. If you open up your water bottle on the top of the mountain, it's going to just look like a regular water bottle. It's closed. There's less air pressure up there. When you travel to the bottom of the mountain, you'll notice that your water bottle, just like a regular plastic water bottle, has collapsed in. That's because there's more air pressure at lower altitudes because there's more air particles, right? So higher pressure is pushing in to the water bottle, okay? We use air pressure when we look at weather quite a bit, as it turns out. The big takeaways with air pressure, so on the most basic level, here's what you need to know. High pressure always moves to low pressure, okay? It's never going to go low to high. It's always going to be high pressure to low pressure. Warm air is less dense than cold air. As the air warms up, it rises and it becomes less dense. So rising air is low pressure, okay? So as the air warms up, it becomes less dense. Low density means low pressure. As the air cools down, it sinks and becomes more dense, right? So when we're talking about heat and density, you can see here the warmer particles are farther apart, the colder particles are closer together. So cold air is dense, warm air is light. It's not as dense. Cold air sinks, warm air rises, okay? As it cools down, becomes dense, high pressure. As it warms up, it rises, it's low pressure, okay? This is a really big concept in how air moves on Earth, and how air moves affects wind and weather and all sorts of things. So we really need to talk about pressure here when we're talking about weather. How does this relate to weather and what we've been talking about, you might ask? Well, a big thing is Hadley cells, and we're going to watch a short video on Hadley cells right here. So just a second. Let's watch our video here.
You know what I've been thinking about lately? Hanging out on a tropical beach with sand between my toes and a cool breeze blowing through my hair. I mean, strictly in the interest of science. Because the breeze in my hair and the wind and even the big cycles going on out there in the ocean are all great ways of understanding currents. A few episodes ago, we learned that the uneven heating of land and water creates wind by forming different pressure zones. The air above the land is warmer and less dense, so it rises, and the air over the water is cooler and heavier. The cool air rushes in toward the low pressure zone over the land, forming a lovely sea breeze. But you may have noticed you don't need a beach to feel a breeze. Nope. Wind is everywhere. Air is constantly moving all around the world in cycles or currents. Sometimes they're small, like a light breeze blowing off the sea, and sometimes they're massive, mighty rivers of wind. Let's see how currents move around the world. You know the Earth is a sphere, so the sun's rays hit the middle of the Earth straight on. This part of the Earth receives direct sunlight. Meanwhile, Earth's poles receive indirect sunlight, or sunlight coming in at an angle. Here, the light is spread out over a larger area and is less intense. This means the Earth's equator is much warmer than the poles. I mean, you wouldn't pack a swimsuit for a trip to the Arctic. And you know that when we have differing temperatures, we're going to have different pressure zones. The area around the equator is a low pressure zone. Here, the warm air rises and starts to slowly move towards the poles. Now, if the Earth weren't spinning on an axis, and if it didn't tilt, and if it wasn't covered in water, then the warm air at the equator would just rise toward the poles and the cool air would move in at the equator, where the warm air just...
Okay, so a big thing just at the beginning of the video here, at the equator, there's more direct sunlight, so there's going to be more heat. That causes the air to rise, right? More heat, air is rising. At the poles, there's less direct sunlight, and the air is colder, so it's sinking, okay? So low pressure at the equator, high pressure at the poles.
Left. This would create two giant air currents called cells. But, of course, things on Earth are causing warm air to rise and the air moves away from the equator, but it doesn't have time to get all the way to the poles. About a third of the way, the air cools, falls, and moves toward the equator again, creating a smaller cell. Another cell is created in the mid-latitudes and another at the poles. In each cell, cold air sinks and warm air rises. There are 6 of these cells circling in the Earth's atmosphere. And at the boundaries of these cells, something really weird starts to happen. We get jet streams. What? Air in these cells is trying extra hard to get from one pressure zone to another, since there's a big temperature difference between the air over the poles and the air over the mid-latitudes. But the Earth is spinning faster at the equator than at the poles. If you were to stand at the Earth's axis on the North Pole, you would spin around more slowly than if you were standing on the equator. So, as air rises over the equator and makes its way toward the poles, it keeps moving eastward at the same rate, even though the higher it goes, the slower the Earth is spinning. This creates ribbons of very fast-moving air called jet streams. Jet streams move in wiggly patterns across Earth caused by the interaction with other high and low pressure systems, and also with seasonal changes too. These streams are usually between 6 to 14 kilometers off the ground and can reach speeds of 442 kilometers per hour. Simple enough. But of course, there's more. We know from our little trip to the beach that there are other factors here. Remember our nice sea breeze? Those small differences between high and low pressure caused by the heating of the land and water taking place on all the coastlines around the world. This makes air patterns even more complicated. And jet streams and wind patterns aren't the only currents.
Okay, class, so there was a lot of information in the last 3.5 minutes, but we're going to focus mostly on how it affects wind on different parts on Earth. So let's go back to our notes here. One of the big takeaways I want you to get is that at the equator, the air is rising because it's warm, right? Lots of direct sunlight. At the poles, the air is sinking because it's much colder, right? Not very much direct sunlight. So you have lots of rising air at the equator, sinking air at the poles. But as the air is moving towards the poles, right? So our high pressure is sinking at the poles. It's trying to move towards the equator. At the equator, it's rising, trying to move towards the poles. As this air is moving towards the poles, it cools off and sinks, right? It doesn't make it all the way to the poles. It cools and sinks. And these cells, there's 3 of them on each hemisphere. These are called Hadley cells. Basically, what they do is you have these cells circulating here different directions. So here it's rising at the equator, and it sinks here at about 30 degrees, and it circulates, okay? So it's moving down towards the equator at the surface. Here in the mid-latitudes, where Minnesota is, your air is sinking right here at 30 degrees and moving up at the surface. So instead of moving towards the equator, it's moving towards the poles. And then it rises at about 60 degrees and moves back down towards the equator, up high in the air, and then it's circulating like this. So big takeaway, at the mid-latitudes, our air is trying to move from towards the poles, okay? So it's moving south to north in the mid-latitudes in the northern hemisphere. It's moving north to south in the southern hemisphere, okay? And finally up here in near the poles, your air is sinking and moving towards the equator, but it warms up as it gets to 60 degrees and does this circulation here. So it's going north to south and then back up and then south to north up in the air. But what I wanted to talk about is how does this affect our wind direction? You guys last week for your one of your assignments was to take wind direction. Well, if you remember, they kind of touched on it in the video. We have this nifty little thing called Coriolis effect, right? So let's go back and find our, well, actually, let's just look at this one here. So let's just look at the mid-latitudes, right? Our air at the surface is trying to go from south to north. But we know that if it's going in a straight line, it's really not going to go straight on Earth because of the Coriolis effect. Because of the Coriolis effect, it deflects to the right in the northern hemisphere. So instead of going straight up towards the poles, it deflects to the right. Now, if it's deflecting to the right and it's trying to move up to the poles, our air is actually going to flow from west to east. And that's why we have predominantly westerly winds. They come out of the west and they move towards the east. When you're naming winds, you always name them from the direction that they're coming. So down here where the air is moving north to south, it also deflects to the right. If you follow this arrow, and it deflects down and to the right, which makes it go east. So we call these easterlies. So here in the mid-latitudes, like where Minnesota is, our air is moving south to north, but it deflects to the right because of the Coriolis effect, and we have westerlies. A lot of you noticed this when you were taking your wind directions last week. So that's why we have westerly winds. That's our lesson for this week, guys. Big takeaways. Rising air equals low pressure because it's warming up. Sinking air equals high pressure because it's more dense and it's colder. This causes our air to flow on Earth, and as it flows, it deflects to the right in the northern hemisphere where we live, and that's why we have westerly winds. Next week, we are going to focus again on weather, but we're going to talk about lows and highs and storms. So next week, we're going to kind of wrap up weather with our last topic, and I hope to see you next week. Again, meeting on Wednesday at 10 a.m.